think the popular phrasing is totally wrong. Quantum physics and gravity go perfectly well as any other theory we know about. One of the biases of the field is that things unify, and we don't really have any evidence for that. I'm actually a champion of a crazier theory.
You've heard it before. Quantum theory and general relativity are fundamentally incompatible. But is that actually true? Or is it something we just say so often we start to believe it? Professor John Donoghue thinks this entire framing is misleading. Gravity is a field, the metric, so you quantize it like QCD. In fact, Feynman and DeWitt did exactly that several decades ago. So what's the actual problem? Donoghue argues it's hidden assumptions. Perhaps something like causality, supersymmetry, or grand unification, even so-called naturalists, could be a human bias rather than an objective law. Today, we delve into quadratic gravity theory and another more speculative theory called random dynamics. On this channel, my name's Curt Jaimungal, and I interview researchers about their theories of reality, most often in physics. And today's a particularly technical talk, so be prepared. I'm excited because you'll see why John Donoghue is a legend in the subject of gravity and its quantization. We'll delve into effective field theory and learn why this professor's judicious restraint unnerves his colleagues. Professor Donoghue, you're known, in a sense, for being radical for not being radical. Explain that.
Well, I am, in a way, quite conservative because I grew up as a phenomenologist where I learned to listen to what nature is telling us. And nature has told us gradually over time that the fundamental interactions are gauge theories, and the gauge theories are composed in particular ways. And we've learned to understand quantum mechanics and the fundamental interactions through interactions with experiment. And so I tend not to deviate from that very much.
You mentioned that quantum mechanics may fail at some point, and when we're thinking of quantum gravity, we're assuming that something about quantum mechanics, whether it's the Dirac von Neumann axioms or something, is held sacred, and then gravity has to bow, in a sense, to those. But you said when we were speaking off air that you don't think that's necessarily true, and I'd like you to comment more about that.
Okay, so the point is that all our theories have limits. We've tested them in some range of energies and conditions, and we're used to thinking of the various interactions as having limits, like the standard model we expect to be supplanted by other interactions. But the same should hold true. We should hold the same standard to quantum mechanics. The standard assumption is that quantum mechanics is valid at all energies, all scales, all everything. Because at present, we don't really need deviations. But nevertheless, there could be deviations both at high energies or on macroscopic scales. And so there are experiments testing quantum mechanics on macroscopic scales, and I think they're very interesting because that's a frontier for the limits of quantum mechanics, and perhaps the theory as we know it now will be changed at some scale, some macroscopic scale. The connection to gravity is that gravity may be the best place to test this because you can get macroscopic bodies out of gravity, whereas it's hard to get very macroscopic charges, for example.
Mm-hmm.
If you're trying to get large amounts of charge, it's hard. Large amounts of mass is easy.
So, sir, when popularizers talk about quantum mechanics and GR are incompatible, are they getting something wrong? And also, I just said quantum mechanics and not quantum theory. So people talk about quantum mechanics, quantum theory, and quantum field theory. I don't know if you see those as different when speaking about general relativity and the combination of those two.
Mm-hmm. Yeah, so I think the popular phrasing is totally wrong. That quantum physics and gravity go perfectly well as any other theory that we know about. Quantum gravity involves a field, which is the metric, That field is quantized. It was done by Feynman and DeWitt in exactly the same way we do QCD. There's no difference at all in the framing of it. So if you just take standard quantum theory and standard gravity, you have a quantum theory. That quantum theory is a little different than the standard model in that it's explicitly an effective field theory, which I can explain what it is. But it's a quantum theory, and it can make quantum predictions perfectly well. That's one of the lessons of the last 30 years.
Now, is anyone of your colleagues thinking that gravity as an EFT for low energies is wrong in some way? It's my understanding that no one would disagree with that.
I don't think anyone disagrees with it at this stage. It took a while for the effective field theory viewpoint to percolate through the field, because many of us grew up learning about renormalizable field theories as the only valid quantum field theories. But that's not true. We have other theories that are effective field theories that we could make perfectly good for quantum predictions with, and general relativity falls in that same category.
Okay, so then are there any problems in quantum gravity that are considered to be fundamental issues, like you mentioned, non-renormalizability, that you think this is a pseudo-problem, it's not even a problem?
Well, it's a problem in the long run if you want a totally consistent theory at all scales. Do you want me to explain effective field theory a little bit?
Please.
So, effective field theory is really just quantum theory with thinking about the scales done right. And the important ingredient is really the uncertainty principle. So in many cases, even in the standard model, there's unknown physics at high energies. So we just don't know what it's about because we've never tested it. But the uncertainty principle tells us that the effect of that is local, because delta E is big, delta X is small, and so it appears effectively local. And so all the unknown effects of very high energy appear as local terms in an effective Lagrangian, in a Lagrangian. And they're just constants that we don't know. There's like the mass of the electron is one of those constants. The charge of the electron is another. The gravitational constant. These are terms that are local. But nevertheless, the quantum effects involve dynamics at the energies you're working at, and those can be done with the degrees of freedom and the interactions that you have at those energies. They're not local in that sense. And so effective field theory basically just separates out the unknown effects from high energy from the known effects at the energy you're working at and makes predictions. And in the end, we think of all of our theories like effective field theories.
Now, you didn't mention the name Ken Wilson, but I think it's probably useful to. So can you talk about how Wilson changed the understanding of what a non-renormalizable theory is? And also feel free to expand on what a non-renormalizable theory is as well, and what the view pre-Wilson versus post-Wilson was.
Right. So Wilson was clearly important in this change in the viewpoint that the point of view that he espoused was that there are various local terms, and the Lagrangian doesn't need to be restricted. So we derive our physics from an action from a Lagrangian. The Lagrangian for renormalizable theories has just a few terms, but in principle there could be terms of higher dimensions, which are, well, I need to explain dimensions, I guess. The Lagrangian that we write out could have many terms. So, if, for example, you could have fields with 2 powers of the fields, 4 powers of the fields, 6 powers of the fields, etc. And those are said to be increasing dimensions. And normally we limit ourselves to the lowest dimensions. Wilson told us that quantum effects generate the other ones also, and that we can include them in the fundamental theory. In the Lagrangian, equally well, we just have to have a way of determining them either by direct calculation or by measurements.
I want to just clarify that the dimensions here, they're not space-time dimensions, they're just powers of the field.
The powers of fields. That's great. Thank you very much. It's so powers of the fields. And so the usual theories that we do, the renormalizable theories, like the standard model, are very limited in the powers of the fields that they use. The effective field theories are more generous. They're more general.
In 1994 or so, you calculated the correction to the Newtonian potential.
Yes.
Walk me through that.
So the interesting insight there is that the long-distance corrections to the Newtonian potential, the ones that fall like a power, since they're not local in the sense, because they're long distance, are then determined not by physics from very high energies, but only by physics from low energies. And we know that physics. So we know that it's general relativity. We know the interactions of general relativity. We know the Feynman rules, because Feynman and DeWitt told us those. And so that the long-distance corrections to the Newtonian potential are rigorously calculable, only knowing what we know at the present energies. And so was a very explicit example of how effective field theories work. By knowing the low energy degrees of freedom, we can make calculations that are valid at low energies without needing to know the high energy theory. There's something that I was thinking that might be interesting to the listeners, of just a perspective on why historically it was difficult to think of a general relativity being a quantum theory. And this is because of the effectiveness of the classical geometric picture. When you learn general relativity, one of the interesting features that you first learn is that general relativity doesn't look like a force. It's straight line motion in a curved space-time. And so you think of a manifold or space-time structure as being fundamental. And there's this sort of mantra that I think probably goes back to Wheeler. Gravity's not a force, it's geometry. And if you come into the game thinking about geometry and not about forces, then gravity does look different than other theories. Other theories have forces and particles mediating the forces. But that's really a feature of the classical theory, and it's not really fundamental. You could equally well formulate general relativity as a theory with exchange particles, with waves on space-time, like gravitational waves that we now detect in LIGO, with exchange particles. And if you formulate it like a field theory, then the quantum theory looks very similar to other quantum theories. If you're formulating in the geometric picture, it looks quite different. And so I think that historically, some of the trouble has come just because the classical theory has been so successful using classical methods that it was hard to switch to quantum methods.
Is there a reason that when I watch your lectures that you start from the you only use the path integral approach, as far as I've seen, and not something else like the canonical?
That's certainly true. I mean, it's certainly true also if you think of x commuted with p being IH bar and all that. It looks much more complicated when x suddenly is a general relativistic coordinate. But all our fundamental theories are now only formulated in path integrals. You can't formulate the standard model in a Hamiltonian theory and use any any reasonably useful formulation. So all our theories are that formulated that way. And general relativity makes the most sense that way. And this is a lesson that goes back to DeWitt in a way. When Feynman, this is a bit technical, but when Feynman showed that you needed ghost fields to get the correct degrees of freedom in general relativity, DeWitt formulated it in the path integral framework. And then the QCD is also formulated that way. So basically, you have to use the same formulation that you use for QCD. You would never do anything else for QCD except path integrals.
I'm sure you've taught quantum field theory.
Yes.
So do you teach canonical quantization at all?
I do. I think the place where in the framework where you're progressing from quantum mechanics to quantum field theory, you need to go through a phase where you define quanta, basically, the original quanta of photons. And so doing second quantization for photons is a necessary step to introducing the idea of quanta. But then at some stage, and so yes, you do that, you define the Fock space, you define one photon, two photon states. At some stage, to do theories like QCD, the weak interactions, you have to get into path integrals and show that they have the same content.
Mm-hmm.
And if you start with path integrals to begin with, it's actually there is a place where it becomes there's a logical disconnect on what is the one quanta state. So there's two very good books that do this. So one is Tony Z's quantum field theory book.
Yes.
And the other is Pierre Ramon's. They start straight from path integrals, but there's a stage in there where there's this logical disconnect of how you define one quanta. And so, yes, I tend to go through the canonical and then show that the same results come out of path integrals.
Earlier, you were saying that most people or most students have heard the geometric interpretation of general relativity, and that can stymie them when thinking about making that compatible with quantum theory. So I'm wondering, are there any other myths or whatever you want to call them that you have to dispel to students?
Well, I think that's the main one. I think if you start with general relativity as a field theory, a classical field theory, then you could merge into the quantum theory quite easily. The trouble is, it does take a while to get there because it takes a while even to get to the quantization of QCD. It's not the day 2 on a quantum course. It's a little further on, and you have to have that background. And so, getting to path integrals has been at least the way I teach it, the best way to get there.
I asked earlier about the tension between quantum mechanics and gravity. Now, should I have said quantum field theory and general relativity, or do you even say aloud quantum mechanics and general relativity?
I tend to say quantum field theory. I probably have not said quantum mechanics. I've said quantum theory, but quantum theory in any relativistic system has become quantum field theory. And so we're talking about quantum field theory, really, when we want to do this.
So has there been any trouble making general relativity consonant with quantum mechanics as such? Or as soon as if you're talking about GR, you're talking about special relativity as a
right.
special case, and as soon as you combine that with quantum mechanics, you get QFT.
Right. So you do have to get to the quantum field theory because for any relativistic field theory, any relativistic system, you need quantum field theory rather than quantum mechanics.
So how do you see then the tension between quantum theory and gravity?
I don't see any tension at the.
Yes, at low energies, sure. But the world is not just low energy.
So at the moment, we know low energies. And so I wouldn't say there's any tension between the standard model and quantum mechanics. There are problems if you try to take the standard model to high energies. For example, if you try to take the Higgs potential at very high energies, there's an instability. So at high energies, the standard model doesn't work very well. We expect it to be supplemented with something else. The same thing's true with general relativity. We expect a more complete theory at high energies. That more complete theory could have various characteristics, but when we think of an effective field theory, we always think of what the limits of the theory are, and the effective field theory tells us that there are limits to where we can apply the effective field theory at high energies.
The Economist covers math, physics, philosophy, and AI in a manner that shows how different countries perceive developments and how they impact markets. They recently published a piece on China's new neutrino detector. They cover extending life via mitochondrial transplants, creating an entirely new field of medicine. But it's also not just science. They analyze culture, they analyze finance, economics, business, international affairs across every region. I'm particularly liking their new Insider feature. It was just launched this month. It gives me, a front row access to The Economist's internal editorial debates, where senior editors argue through the news with world leaders and policymakers in twice weekly long format shows. Basically, an extremely high-quality podcast. Whether it's scientific innovation or shifting global politics, The Economist provides comprehensive coverage beyond headlines. As a TOE listener, you get a special discount. Head over to economist.com/TOE to subscribe. That's economist.com/TOE for your discount. So the string theorists are concerned with UV completion.
Right.
And they believe that you would require some extended object. So do you disagree with them, or is your disagreement more empirical or philosophical, or what?
I don't think there's a disagreement between the string theory approach and the effective field theory approach. String theory is one possible UV completion. And it's interesting because it's one where we have the most calculational control. So it is useful to see what a complete quantum theory of gravity could look like. And as far as I can see, that it should match onto the effective field theory in all the regions where we expect them to both overlap. And so I don't see any conflict there.
There's something called the swampland conjectures.
Right.
I'm sure you've heard of. So does EFT gravity or quadratic gravity sit in the landscape or in the swampland?
So EFT has a set of parameters which are undefined by the EFT. And there is a portion of those parameters that live in the swampland and a portion that live in the non-swampland. So the swampland program basically divides the EFT parameter space into two regions, swampland and not. We can do quadratic gravity if you want.
Sure, I would love to hear about that.
The Einstein's theory follows from an action that's, let me neglect the cosmological constant and all that follows, just follows from a very simple Lagrangian, which is just the scalar curvature. So if you take the scalar curvature, it has to be a general covariant and Lorentz invariant object. There is one simple one, which is just the scalar curvature by itself, that gives you Einstein gravity. However, consistent with all the things that I've just said, you could also take the scalar curvature squared. That also works. So that's when we say quadratic, that means curvature squared. And it turns out there's two terms. One, there's the scalar curvature squared, and the other is the Ricci curvature squared, or the Weil tensor squared. There's two possible terms at quadratic squared.
I'll show the Lagrangian on screen.
Okay. Then the beauty of that is if you do that, the theory becomes renormalizable. And so it fits in then with all the other theories that we know as renormalizable quantum field theories. And that was shown by Stelle back in the 70s. So it's singled out as a particularly nice theory, a very conservative theory where the metric is still the main degrees of freedom. The theory is renormalizable, and it's essentially unique in that. So this is the theory that I have done some work on in the past 10 years or so with Gabriel Menendez, my collaborator, and others in the field that are also exploring this.
There's a but here.
There's a but. Okay. And the but is that the reason this works is that the curvature involves two derivatives of the metric. The curvature squareds then involve four derivatives of the metric. And when you go from two derivatives to four derivatives, things happen that aren't part of the usual axioms of quantum field theory. In usual axioms, the requirement of analyticity restricts you to two derivatives. When you go to four, then something falls apart. And there's been a lot of debate on what it is. It could be unitarity, it could be causality, it could be stability. My sense is that at least in path-random quantization, the theory is unitary, it's stable, but it does give up causality at high energies. And the reason for this is that analyticity, this assumption of analyticity, is also tied into the usual requirements for analyticity.
Wait, analyticity is required for analyticity? You mean for causality?
Analyticity is required for causality. I'm sorry.
Yes. Okay, so are you referring to Ostrogradsky or something else when you say that there are instabilities?
So the stability is Ostrogradsky. So there's the classical theory, if you put higher derivatives in, exhibits an instability which was shown by Ostrogradsky almost 200 years ago. However, there's a reasonable number of ways that we feel that is not true in the quantum theory.
Interesting.
So I think that Ostrogradsky, the instability is not an issue. This seems to be a stable theory. One indication is that these higher derivative theories can be simulated on a lattice without showing instabilities. As far as I can tell, the theory seems to be stable against decays, to be stable, to lower energy states. It does require a particular sign for a coupling constant. So there are three coupling constants in the theory. They have to take particular signs, and one of the signs is particularly interesting. And the reason they have to take signs is partially the stability issue. There are new states in the theory, and if you choose the sign wrong, you get tachyonic states, and those ordinary matter will just decay into infinite number of tachyons, and you'll be unstable. So there is a sign choice involved.
Why don't you give the viewer an intuitive understanding of quadratic gravity? Because when you have just the Ricci scalar and you vary it, you get the Einstein equations.
Right.
And then that has some intuitive picture that people like to espouse of geometry and geodesics and so forth. So what changes when you add these quadratic terms to the intuitive picture people have of what general relativity is?
Well, so low energies would be the same picture. These quadratic terms are negligible at low energies. So everything that we've tested experimentally would be the same. The trick only happens when the curvatures or the energies are very large. And then the fact that the curvature involves two derivatives, curvature squareds involve four, derivatives turn into energies, meaning that if you have high curvature or high energy, the other terms dominate. You would still have a geometric theory, but it would satisfy different equations. They would be fourth-order differential equations. For the quantum theory, the important part of that is that normally with two derivatives, propagators for particles go like 1 over the energy squared. Four derivatives, it goes like 1 over energy to the fourth. And so what changes is that all the high energy stuff becomes better behaved because the 1 over energy to the fourth kills off high energy divergences and makes things renormalizable. And so the fact that it has four derivatives is crucial to making the high energy theory well behaved. So in contrast to general relativity, where the high energy theory has bad behavior, here the high energy theory has good behavior. Just like QCD, for example.
What about singularities? Does it give any insight into singularities?
Yeah.
Or black holes or the Big Bang or what have you?
It's a good question. And I don't think the answer is completely known at this stage. It's not even clear that the question is well posed, because at high energies, it's not clear that you should be using a simple classical picture. And the singularity theorems are all classical theorems.
Mm-hmm.
There are work by Bob Holdham and Stelly and collaborators that show that there are non-singular black hole solutions that come out of the quadratic gravity case. So there's not a clear understanding of which one should be selected, but certainly there are non-singular solutions to quadratic gravity.
Interesting. Earlier, when you said that general relativity can be formulated as a force theory, not just as a geometric theory, like Wheeler suggested, are you referring to it classically or are you referring to it quantumly?
Both.
How can it make sense as a particle theory classically if it's a field theory?
So, for example, there's now a whole body of a whole subfield where they treat black hole mergers using quantum field theory techniques. And basically, there's a classical limit that you can take of doing Feynman diagrams. And you could pick out the quantum effects of the classical effects, of black hole mergers. It started with work by Goldberger and Rothstein and has now become a much larger field, including some of the people that use standard relativity techniques for a long time. It very quickly caught up to the other techniques using differential equations.
Equivalently, just as you said that GR can be formulated as a force theory versus curvature theory, I'm sure you've heard that you can add torsion and then formulate general relativity as a torsion theory, Einstein-Cartan theory, or you could turn on non-metricity with metricifying. Right. So there's all these different little tweaks that you can do to GR to get an equivalent theory. Is there anything about quadratic gravity that would rule out torsion or non-metricity?
No, I don't think so. I haven't explored the extensions that much, but the extensions using torsion and non-metricity do exist, and people have done some explorations. I think it's a great exercises. For me, quadratic gravity is the simplest version, and it's in some ways the most conservative because it doesn't do anything beyond what we know we need. We already need. We know that we would expect a curvature squared terms to be in the action. And so we're just using them in the minimal way.
I'd like to talk about causality.
Okay.
So you have a phrase that there are dueling arrows of causality.
Right.
That could be yours or your collaborator, Menendez. What did you mean by that? That there are dueling arrows of causality?
So this is what I referred to earlier in that when you do this theory with four derivatives, any theory with four derivatives, you give up some portion of the usual axiomatic field theories. And it seems that at least with path integral quantization followed the usual pathway, that what you get is you're giving up some aspects of causality. And that aspect is the following. There is an arrow of causality that's built into our theories. And that's contained in the factors of I in the quantization procedure. If you do path integrals, it's e to the is, e to the I times the action.
Mm-hmm.
If you chose e to the minus is, you would actually have the exact same theory, but just a different arrow of causality. Things in positive time would influence things the later in negative time. It basically, time reversal changes I to minus I. Its time reversal is anti-unitary. And so if you take e to the is and do time reversal on it, you get a time reverse theory that's exactly the same. And the nature of the theories with higher derivatives is that you get a massless, in the case of gravity, a light particle with the usual arrow of causality and a very heavy particle with the opposite arrow of causality.
Okay.
So if you produce this guy, if you come in with positive energy, it propagates not forward in time like normally does, but it propagates backwards in time for a short period of time. It decays, you then get normal particles out, but you've had a short period of time where this thing propagated with a different direction in time. Which is takes a while to wrap your head around, but at least I've come to peace with it.
Why does it take some time to wrap your head around?
Well, so we're used to the idea that particles can propagate to the left, particles can propagate to the right when they're carrying positive energy. However, the standard theory is if you have a positive energy particle, it only propagates in one direction in time. Propagating in the backwards direction in time doesn't normally occur. And that is because we use e to the is as the in the path integral. It's equivalently if you do commutators with IH bar as opposed to minus IH bar. And so we're not used to seeing, in this case, when you decompose the interactions, you get the light particle with e to the is and the massless, the heavy particle, the ghost particle, with e to the minus is. And let me make a caveat, just to be honest. The theory that has this seems to work. We've been able to do one loop calculations in it. I think it's still not clear how one does higher loop calculations, and we don't know for sure that it works at all orders, which is one reason for exploring lattice calculations. And so I shouldn't say that it's known to be without flaws, but it's known at some order in perturbation theory.
Does the S matrix assume causality?
So the S matrix defines the transition from stable states in the past to stable states in the future.
Right. Well, if light cones are somehow fuzzy, then that's what I'm wondering is what would be considered in versus out.
Right.
And how do you define the S matrix?
So in this case, all these heavy particles that have the funny propagation are unstable. And so they don't live in the distant past or the distant future when you do define an S matrix. They just live as intermediate states. So you go through a region. So you imagine doing a scattering, you take usual particles in, you scatter them. Some have resonances that go to heavy particles that are normal particles. Some have these funny ones that propagate backwards for a short period of time. But then you end up with all your normal particles in the future. So the proof of unitary that Gabriel and I did it makes an important feature that only normal particles live in the distant past and the distant future for the S matrix.
Does this mean there was something non-local occurring at the Big Bang?
I don't know how to answer that. I mean, I don't know the answer. We are trying to look at some of the implications for the early universe, but it's not really clear how one defines the start of the universe in any theory. We could describe it accurately after a certain phase where the physics that we know kicks in, but I don't know what starts the universe.
You told Quantum Magazine that you're not convinced that quadratic gravity is the final theory.
Right. So, but that's much like the Standard Model in the sense that I also don't, the Standard Model I don't expect to be the final theory. In the case of quadratic gravity, it feels to me like the Standard Model. It feels like it's a renormalizable quantum theory that would kick in at some scales, much maybe the scale of inflation. And for those scales, it would be a perfectly fine theory. But at that level, we have the Standard Model, which has three separate theories involved. We have a renormalizable theory of gravity. That doesn't feel like the final theory to me. It feels like something else is going to explain the origin of all of these theories. And so I expect, or I would naturally expect, that there's some deeper theory that explains the Standard Model and gravity both. And string theory is a possibility. That's perfectly fine. It could be something else. I'm actually a champion of a crazier theory, which is Holger-Nielsen. Holger-Nielsen had this crazy idea that at very high energies, everything happens. So basically, you can imagine everything you can imagine happening. And it's sort of, he calls it random dynamics. And that the reason why at low energies you only see certain theories is that some theories are protected and are able to have massless fermions, massless gauge bosons. So gauge symmetry and chirality protect fields from generating masses. So if you gauge bosons, it's probably well known. Chirality is probably less well known. That for fermions, if you have chiral fermions, you have a left field by itself. It can't have a mass. And so his argument was that the reason we see at low energies the Standard Model with chiral fermions and gauge fields is that the only ones that are protected at low energies from generating large masses. And therefore you get U1, SU2, SU3. And by the same logic, you could get a gravity theory that is protected by a general covariance from having larger masses. And so this is sort of the anti-unification. Instead of unifying, you have everything happening at high energies, but only some things living to low energies. I just like it as an idea.
Okay, this is super interesting because you're so conservative in terms of you don't want to posit more than necessary, but then over here you're extremely attracted to something that is quite zany.
Well, this is a bit, yeah, it's a bit contrarian. I have to say if you search yourself for biases, one of the biases of the field is that things unify. And we don't really have any evidence for that. There's no evidence for gauge unification at all. People normally talk about unifying electricity and magnetism, but that's not really two gauge theories. What you've done is you've identified the single gauge theory that describes both those phenomena, U1. And the electroweak unification isn't really unification. You started out with E&M and a weak theory, and you've explained it by having two theories that mix, SU2 cross U1. They're not unified, they're just mixing.
Uh-huh.
So that we've never really seen unification. So the idea of unification could just totally be a bias. It could be that the theory as we go up in energies is U1, SU2, SU3, SU4, SU5, SU6, SU7, or something else as you go up. It doesn't have to ever come together into a unified theory, a unified gauge theory.
Yes. Okay.
So this I like the random dynamics idea mainly just because it's an example of how our biases may be making us miss what is the ultimate high energy theory.
Okay, so at first when you were saying that there hasn't been unification, you qualify that with gauge unification.
Yes.
So because the standard folklore that people hear is, well, there was the heavens and the earth and Newton unified that with gravity. Then there was space and time, and then Einstein unified that with space-time. And then there's electromagnetism or electricity and magnetism. They're unified and so forth.
Yeah, those are just identifying the appropriate interactions. That's not a unification of any interactions. E&M, electricity and magnetism look like different phenomena, but we've actually, Maxwell, you find out that it's really the same underlying theory, just one theory. So if you want to use the word unify, it's okay, but it's not unification in the sense that the particle physics field assumes is going to happen at high energies. We assume that we're going to merge into some SU5 or SU10 or E8 cross E8 or some unified theory with more degrees of freedom, but which has a higher symmetry than what we have at the moment. That's a beautiful idea. It's a great idea. I'm not saying it's wrong. I'm just wondering if that's a preconception that keeps us from seeing other options.
So you're not saying there's something inherently wrong with guts,
No.
with grand unified theories.
Yeah.
You're saying that there are alternatives. Or maybe you are saying there's something wrong with guts.
One of the lessons of the LHC may be that there is something wrong with guts. Because the reason that we, as a field, were so convinced that something was going to happen at the LHC basically went back to a conflict with the idea of grand unified theories. In grand unified theories, you have this very heavy scale, and the symmetry is broken, and the need is to have the electroweak theory happen at a lower scale. But in a grand unified theory, that's a very unnatural thing to have happen because you have the naturalness argument says that the electroweak scale would naturally be very close to the grand unified scale because radiative corrections generate large effects and would normally bring it back up. So the naturalness argument led us to believe that there was some mechanism that protected the electroweak scale and kept it at low energies. And this, for example, was supersymmetry. The argument for low energy supersymmetry basically came from trying to protect grand unified theories from large radiative corrections and allow the electroweak scale to be very much less than the grand unified scale. However, we've learned from the LHC that doesn't happen. There is no evidence of supersymmetry at the LHC. And so if we really believed our arguments about naturalness, the conclusion should be that there shouldn't be any theory, any high-energy theory that has a naturalness problem. And so there shouldn't be grand unified theories.
I'm just shocked because I entered into this conversation with you, and probably you the same, thinking that this would be one of the most, not ordinary, but uncontroversial
Well,
podcasts that I've had,
okay.
or podcast guests. In fact, I even started it by saying that you're known, in a sense, for the radicalness of you, if there is any radicalness, would be that you are not radical in a place where you can see your colleagues as engaging in some speculation where it may be unwarranted in your frame of mind. Okay. And now we're getting to something that philosophers called enthymemes. I don't know if you've heard this term, enthymemes.
Not particularly, but
An enthymeme is an argument with an unstated premise. So it sounds to me like you're attacking some of these unstated or hidden. There are these assumptions that are so widely held, like that grand unification is going to occur, that we have supersymmetry, and that unification, even that, the fact that you say that unification also may be something to be questioned.
Correct.
But you're talking about a particular kind of unification. That's super interesting. So I want to know.
This is something that we should be doing. And in a way, it actually relates to our starting topic, which is one of the unstated assumptions for decades was that general relativity and quantum mechanics were incompatible. One of the things everyone should be doing at every step of the way is questioning these assumptions and seeing if they're based in fact or are something that's keeping us from progress. And in the case of the general relativity, the effective field theory techniques told us that assumption was in fact incorrect. And so we're just continuing to do that. The quadratic gravity is questioning whether an assumption of analyticity and causality is valid at all scales. So I'm doing it again with unification.
What if a string theorist says, look, string theory uniquely gives a finite 2-to-2 graviton amplitude at all orders? Is that not evidence that string theory is on the correct track?
Well, it does that with some assumptions. I think if it really was proven to be unique with absolutely no exceptions, then that's a powerful statement. I think that's unlikely to happen. I mean, one of the assumptions of the string theory program is causality holds at all scales, and so if I give up causality, I could probably get a perfectly fine amplitude at all energies. And again, so some of the assumptions that we've made at high energies are built into the theories that we're constructing, and they may be correct. I'm not saying that it's incorrect, but it's also possible that there are alternate ways of completing a high energy theory that I would expect is not unique to string theory.
Do you have advice that you consistently give your students?
The biggest advice I like to give my students was to read widely and think about things outside of their own research areas. In practice, what I say is to, when you're reading papers, read the introductions and the abstracts, so that you get a sense of why people feel things are important problems and what approaches they use. And then just to keep thinking about things outside of your own research area. Because you're not going to be doing your thesis topic the rest of your life. Everyone is going to move on from their thesis topic, and they have to find the richest pathway to having a long career. So I started working on the quark models, ended up on quantum gravity. So it's quite a distinction.
So when you say read outside your research area, you don't mean to say that if you're a physicist, start looking into biology.
Well, if that interests you, I think you could. There are many people that have made interesting transitions from physics, theoretical physics, to biological physics. If that's an interest of yours, I think that's a wonderful thing to do. But I do tend to mean if you're working on electroweak phase transitions, that you should also read up on grand unification and string theory. Get at least a basic understanding of the whole field as a whole. Your particular research topic, you're required as a student to become an expert on a very particular topic, and you really need to do that. But you also, for future success, need to look outside of that. And I think many successful theorists do that early in their career too. One of the things that I've always done when I'm on search committees looking for faculty members is to see if they've done anything that's not exactly their thesis work. So they have often are said to be one of the top people on subfield X, Y, or Z. But then many people have written papers or had little collaborations that are outside of that. And that's always a positive sign, because it shows that they're interested and able to contribute to more than one area.
Professor, are there any lessons that you wish you'd learned sooner in life?
In some ways, I guess it would have been nice to put my own advice into action a little sooner, and that working on some of the other areas earlier in my career, I think, could have been fun. But then again, I don't regret anything particular. So, I probably could have done the effective field theory 6 or 7 years earlier, of gravity 6 or 7 years earlier. I basically knew the general principles at that stage from doing effective field theory work. To do the correction to the Newtonian potential, I knew was going to be a very long calculation with a result that's not able to be measured. And I was pretty much a phenomenologist at the time, and so I'd like to do measurable things. So I put off doing it until at one stage I decided I just needed to do it. But I could have done that six years earlier. Might have been fun.
What idea of yours has faced the most resistance?
Well, I was on this anthropic bandwagon for a while. The anthropic stuff has tremendous resistance by large numbers of people.
But you are no longer? I know you had a 1998 paper on it.
No, I don't. I just don't see anything that I usefully can do at the moment. I sort of read out of useful things to do. I still think it's one of the pathways to a fundamental theory that makes a good deal of sense. Again, it's part of this questioning the hidden assumptions that we're doing, is that we grew up thinking that there is a unique theory, the grand unified theory in particular, that was going to explain everything, give us all the masses and coupling constants of the theory of that we see in nature. And the anthropic ideas make that actually seem very unlikely. Just such a small portion of parameter space that it's consistent with existence of stars and atoms, that it seems to be almost a very unlikely possibility.
Speaking of hidden assumptions, are there any hidden assumptions that your colleagues or perhaps even your students have questioned that you said That's a bit too far. I wouldn't question that.
My attitude on that is I would probably never say it, but I'd ask if they could do anything useful with it by questioning it. If they would like to give up 4 dimensions, fine. Do something with it. So I guess I wouldn't ever say,
Not out loud.
Don't go there, but I'd say whether it's a profitable thing to do, to suggest.
Sir, it's been an honor to speak with you. Thank you.
Very good.
Hi there, Curt here. If you'd like more content from Theories of Everything and the very best listening experience, then be sure to check out my Substack at Jaimungal.org. Some of the top perks are that every week you get brand new episodes ahead of time. You also get bonus written content exclusively for our members. That's CurtJaimungal.org. You can also just search my name and the word Substack on Google. Since I started that Substack, it somehow already became number 2 in the science category. Now, Substack, for those who are unfamiliar, is like a newsletter, one that's beautifully formatted. There's zero spam. This is the best place to follow the content of this channel that isn't anywhere else. It's not on YouTube. It's not on Patreon. It's exclusive to the Substack. It's free. There are ways for you to support me on Substack if you want, and you'll get special bonuses if you do. Several people ask me, like, hey, Curt, you've spoken to so many people in the fields of theoretical physics, of philosophy, of consciousness. What are your thoughts, man? Well, while I remain impartial in interviews, this Substack is a way to peer into my present deliberations on these topics. And it's the perfect way to support me directly. CurtJaimungal.org or search Curt Jaimungal Substack on Google. Oh, and I've received several messages, emails, and comments from professors and researchers saying that they recommend Theories of Everything to their students. That's fantastic. If you're a professor or a lecturer or what have you, and there's a particular standout episode that students can benefit from, or your friends, please do share. And of course, a huge thank you to our advertising sponsor, The Economist. Visit economist.com/toe, TOE, to get a massive discount on their annual subscription. I subscribe to The Economist, and you'll love it as well. Toe is actually the only podcast that they currently partner with, so it's a huge honor for me, and for you, you're getting an exclusive discount. That's economist.com/toe, TOE. And finally, you should know this podcast is on iTunes, it's on Spotify, it's on all the audio platforms. All you have to do is type in Theories of Everything and you'll find it. I know my last name is complicated, so maybe you don't want to type in Jaimungal, but you can type in Theories of Everything and you'll find it. Personally, I gain from rewatching lectures and podcasts. I also read in the comment that Toe listeners also gain from replaying. So how about instead you re-listen on one of those platforms like iTunes, Spotify, Google Podcasts, whatever podcast catcher you use. I'm there with you. Thank you for listening.